So learning is changing this value, W. Finding slope, for example.
That is the, what is the capital one?
This
It's not the capital by so wide.
yes, sorry for symbol notations. I some this.
What does the slope mean?
The slope of this red line.
The capital S was a vector.
Yeah, yes. Actually, it can be vector. In this case, it's just schematics. In this case, X is one-dimensional, but usually X can be higher dimensional.
So each vector is of capital N dimension. Is it?
P dimension.
P dimension?
Yeah.
P dimension.
And there are N set.
N set.
Yeah. Yes.
And then the horizontal, the number means what? Does it mean?
That is just a symbolic meaning, just X values. X values. Small x, this should be small x. So yeah. This one.
Because I don't understand the slope.
In this case, I draw the minimal version, one-dimensional version. X is one-dimensional, W is a number in this case. But in general, this can be vector. This can also.
And what you're showing is that if capital is larger, then you are having in more prior function W. Okay, right? W is what you try to get as a solution.
Yes.
Which gives the product value Y.
Yes.
And so naively speaking, if the capital N is bigger than P,
Yeah.
or even at the same value P, then we can at this invert the matrix and we can exactly solve.
Yes.
But what you're saying is that it is not true, and if N is larger, capital N is larger, then arrow grows, then the suddenly comes down.
Yes. So it, depending on the ratio, or there can be some exact solutions, but sometimes you cannot solve it. And
so the test error is growing as a function of capital N instead of just test error. You define test error.
Yes. So capital in this case, capital N is fixed, but P is changing. But we can change the role. You can fix the P and change N. The important thing is the ratio P over N. So when P is equal to N, error diverges due to diverging variance. Bias is small. So this is the interpolation threshold. And over this point, error decreases again. But we don't know the reason so far.
Is it obvious that error is the maximum at any point? Is it obvious?
There are some models, it's not obvious.
So usually overfitting means simply that you store the data into the weights. So you memorize the data into the weights, but you have no predicting power.
Yes, right.
In other words, you just convert the data into the weights of your model without learning anything. So now you're saying that instead, when you have a huge amount of weights, a huge amount of parameters, then you have the model works again.
Yeah.
And you don't understand why.
Yes.
Because in principle, the weights are completely undetermined. You don't have enough data to determine.
Yes, sir. Something like that. Something like that. But there is
So
no.
you should have the generous.
Yeah.
The same weights should predict the same. So the same data should be predicted by very different sets of weights.
Yeah.
But for some reason, it works again.
Yeah.
And the claim is that this is where AI works,
Yeah.
but it's not understood why.
Yes. That's the point. So maybe we PCs can solve this problem. Yeah.
So train or test error is how roughly it is defined.
Train in machine learning, we use some set of data for train. Then we can test the trained result using another set of data.
Mhm.
So test error means the error with another data, another new data. Train error means we use same training data for estimate error. We can use.
In other words, when you have overfitting, the model it is only able to predict the training data. When you provide new data, the system is not able to predict. It's like a student who memorizes only one problem, he can solve only that problem. You give a different problem, it fails. Because it just memorizes that particular problem. This is all. So the data are just stored in the weights, and the model is only able to predict those data because they are just stored in the weights. And then it's really puzzling. So
Yeah.
this bearing over 50 is really puzzling. It's puzzling.
Puzzling.
So,
Puzzling. Yeah. Usually they think this overfitting is due to fluctuation. This machine learning is too sensitive to the fluctuating input data. Something like
the overfitting is very easy. You can generate some random data. You make a model that fits the random data, and it works perfectly. And then you give other data, it is not able to predict because the data has no information. It's random.
Yes.
So it's very easy to produce an overfitting.
So FLN is roughly number of training,
number of data.
number of data with which you will train. So it's a different some number of training. It's given by some set of weight, W.
Yes.
The
parameters, P measurement parameters.
So basically, when you have a huge number of parameters compared to the data, for some reason the model works again.
Something like total input data. N is total input data. Something a number of input data.
So somehow, if there are so many data, capital N large, then somehow it does not work well.
Yes. Relatively. Maybe President Kim can answer later. I am not expert in this field.
Interestingly, we can see the figure middle of the page when the number of parameters is 50. This is the overfitting situation, right? The middle one, not the
No.
yeah. So this is the overfitting situation, right?
Yeah, that's
So
right.
interestingly, we can see that some points in the middle of the figure is very well fitted.
Yes.
So does it?
But you're fitting.
But these are very
So
bad fitting.
that middle part represents some kind of piece very larger than n, right?
P is equal N.
And for a very small number of points, it fits to the data.
These points are data.
Yeah, so the overall fitting status is very bad because this is overfitting.
Yeah.
But when we consider only small portion of points,
Here?
that fits very well.
Right.
So that can be an evidence for the naive probe of when the situation becomes like is very larger than n, it can be very a good fitting, right?
So maybe.
It's different story.
Right?
Yeah,
Totally
yeah,
different?
yeah. Just fitting the data is training error. The goal of the AI is to minimize the test error. Goal of AI is to minimize test error. You mentioned about training error. It's different. Because at the critical point, usually data itself has a intrinsic error. So the parameter learn the error itself, given error itself. That's why a critical phenomena happens there.
He's saying that training error is error between this red line and this blue point. And test error is error between U point not on here, and this red line.
Interestingly, benign means you can see that the fluctuation is somehow smaller than the critical point. And you can see that the red curve does not touch every blue point. That's the point. That's the puzzle, and that's the working function, some secret for the AI.
So 2 degrees test error, it satisfies some input data. Now we can move to black hole information paradox. Sorry, yeah. And as you know, black hole information paradox is about the recovery of matter dumped into the black hole using Hawking radiation. And we need a quantum computer to recover the information. This page curve will represent the information, the puzzles. And this green line shows the entropy of Hawking radiation by Hawking's semi-classical calculation. But entropy of radiation and that of black holes, if they start in a pure state, should be smaller than the area. So as the time goes, at some point, this entropy of radiation should decrease, unlike Hawking's calculation. There is some contradiction here, even in macroscopic black holes. And this turning point is called phase time. So to save the unitarity, radiation entropy should satisfy this curve, this phase curve. Many argue that if you can find phase curve, you can solve the paradox. In this stuff, black hole has exponential as degree of freedom. S is entropy of black hole. Omega is the dimension of the Hawking radiation. In scenario A, according to Hawking, the number of Hawking radiation it become large, and their entropy increases monotonically. But at the last time, there is nothing inside the black hole with which Hawking radiation coupled. So it is puzzling. So usually people are thinking that information inside the black hole came out as a correlation between Hawking radiation, represented by red lines. Entanglement. These are entanglement. in this way, you can decrease the entropy of radiation because of
What is the essential difference between A and B? Actually, they are all of them are actually entangled to the same situation.
yes,
B, what is the difference from
he
A situation?
assumes that in this case, Hawking radiation are entangled with the internal state of black hole. And at the last time, there is nothing left here, so it's puzzling at this point. But in this case, nothing, there is no remnant in black hole. And all the information is in different configuration of entanglement.
You mean in a case, actually, entanglement arises from the inside and outside region?
Yes, yes.
And the B case, actually, outside region.
Yes,
Only
outside.
In the second case, the entropy is lower.
Page. So outside the horizon, only red particles are entangled.
Yes.
Outside the front.
So what we are suggesting is that this page curve is very similar to double descent phenomena. Both page curve and variance of double descent show transition around the alpha equal 1. Alpha in black hole is omega over exponential to the s. The dimension of radiation over dimension of black hole, internal degree of freedom. This ratio is alpha. And in machine learning, this is parameter of data. This peak is related to this peak.
So the distance of the page time should it be derived from quantum perspective, not the classical or sample perspective?
I think nobody knows that point. In this case, we can use semi-classical gravity here. It is large, but I wonder we can use semi-classical gravity to derive this curve. I don't know.
Page time is essentially classical concept. Yeah. The time when the black hole entropy reduced half, actually. Yeah, that's the time.
Yes.
So in the bottom figure, there is no A branch from the Hawking computation.
A branch.
Yeah.
Yeah. Yes. Right. A branch is something like this. They expected something like this. They computer scientists are surprised to see this too. Sure. And what's the relation between deep learning and black hole? As you know, Heidi and Presky show that when black hole cross through the space-time, after the space-time, if you put a book into the black hole, then you can recover the information of the book using late radiation. And if you keep the early radiation too, that's the that works only after the page time. Before the page time, you cannot do that. That's the hiding Presky. This is called black hole as mirrors. In this case, we should assume material has a perfect control of the emitted radiation and perfect knowledge of the dynamics of the black hole.
Essentially, after page time, actually they are maximally entangled.
Yeah.
So observer A observe actually a radiated quanta. Then if they are entangled, then as you know from the EPR experiment, if we observe one particle state, and the others are automatically determined.
Yes.
So in that sense, at the page time, if I observe outside the region of particle state, then I think we know everything. Is it right?
I think so. I guess so. Yeah. Something like that. I think so. Yeah. Yeah. So
Why then we need to actually after page time, you introduce actually additional time, scramble actually hidden prescript. After page time, you are discussing to resolve the information paradox. Right? So my
Yeah.
question is,
Yeah.
just at the page time, everything can be resolved.
yes, at this point, like in 2007, yeah, it looks solved. Yeah, here. So in this case, black hole acts like
I'm wondering why they need prescript, hidden prescript decoding protocol. After page time.
I think
At page time, actually, they are maximally entangled. So outside the region, observer can detect the quanta outside. Then they are entangled. From the EPR experiment tells us that we know the other state, particle state.
yes, yes.
Yeah.
So I think they just show it works. This page curve can work to retrieve information, something like that. And then, in this work, they used scrambling time, and based on MSS work, they show that the approach to explain it is something like a chaotic system, and is bounded by temperature. And using this bound, they computing the scrambling in time. So after page time, scrambling time is short. Escape time is about scrambling time. So recovery from Hawking addition is possible via decoding, something like error correction, quantum error correction. Then firewall paradox. They attacked this protocol. They assume that unitarity, radiation and black hole is unitary. The total entropy is 0. No drama. The horizon is local vacuum. You can use semi-classical gravity. And after page time, the remaining black hole is nearly maximally intelligent orientation. But this looks obvious. But this leads to strong contradiction via strong subadditivity. This relation is from quantum information, well-known result. After page time, this becomes this is very small, and B prime is small, so you can change it to SR and something like that. Then you can derive this relation, but B prime is small, but SR is not small. It is summary. So there is contradiction. It is just one of the form of paradox. You can use another additivity. So they argue that the assumption, all these assumptions cannot be true simultaneously, and they argue that you can give a no drama. There is a firewall And
So do you mean that you can resolve the firewall product by this language? You just state that what is the firewall problem?
higher problem, if we use this, if we accept these three assumptions, there is contradiction from integrament to monogamy. That means black hole and early radiation has a strong entanglement, and early radiation and the late radiation is entangled strongly, but single system cannot be maximally entangled to other two systems. That's the theorem from quantum information. That is called entanglement.
You can describe the firewall paradox by this language?
Yes, yes. So this assumption violates this strong solver additivity. It is just a mathematical.
Professor Kim, you are the expert on the firewall paradox.
Where is the firewall? What is the firewall here? The firewall appear at the horizon.
Yeah.
Yeah, so how to know?
So, after this, there is no firewall. There is just contradiction.
Yeah,
And they argue that you can give up number two. And that means this entropy is large. This entropy can be large. Then that is horizon is hot.
What do you mean smooth horizon? Smooth horizon versus information recovery. But smooth horizon.
Smooth horizon means no drama.
No
Yes.
drama means general covariance.
Yes, yes, yes.
Then general covariance or unitarity.
Yes.
Then it means if you insist unitarity, then the firewall appears.
Yeah.
If you accept the smooth horizon, then the information recovery phase.
Yeah. This argument is very strong, so how to avoid it? Then Harlow-Hayden complete argument. But they think Harlow and Hayden think that there is a loophole in this argument. To check this inequality, you need to extract entanglement from the radiation to check the radiation. So you need a quantum computer, kind of. But they argue that this, even if information is in late radiation, decoding it using quantum computer is computationally intractable. It takes exponential time. So this resolution is very different from ordinary one. Decoding time is larger than evaporation time of black hole. So outside observer trying to check the entanglement, it takes longer time than the life of black hole itself. So there is no chance to check the violation. So no observer can decode information in time to encounter the corresponding pattern mode. Resolve firewall paradox by appealing to computational complexity, not quantum mechanics violation. This is quite strange.
So the information is there, but you cannot collect.
Pardon?
The information is there, but it takes an infinite time.
Yes, yeah.
Cool.
Yeah. Hawking radiation has all the information, but if you extract the information from Hawking radiation, it takes too long time. longer than the life of the black hole. So there's some at first glance, it is very strange. What is the relative to physics to computational science, right? Now again, move to double extent. What is the origin of double extent? There is no resolution so far, but one idea is this one. This is the input picture matrix. You can use singular value decomposition and get the eigenvalues. And this test data can be in a linear regression can be expressed by this formula. And if minimum eigenvalue is very small, then this error becomes large. So this interpolation threshold corresponds to this zero eigenvalue. That's the one of the idea. All these are relative to so-called Marchenko posture distribution. What is the MP distribution? Let X be a random matrix with the independent identical distribution, having mean 0 and variance 1, and then define covariance using X. As n and p goes to infinity with alpha fixed, the eigenvalue distribution of this covariance converges to a unique distribution, so-called NP distribution. For example, when alpha is small, alpha is less than 1, it has broad band. And when alpha is equal to 1, zero mode appears. And this is relative to the diverging error. And when alpha is larger than 1, there is a gap between zero mode and continuous spectrum. I think we need to teach NP distribution in mathematical physics class. It is very universal, but I didn't know this NP distribution before President Kim teach me. If you have a random matrix with this property, always NP distribution forms. Using this NP distribution, you can calculate the variance for linear regression. In linear regression, the second descent is not clear. It rises again, but due to too much linearity. But essence is similar. In linear model, you can use training data, and the goal is to find the weight W. This weight is the slope in the linear case, but you can imagine that this is the parameters of deep learning neural networks, linking nodes. Changing W is learning. So you can derive the solutions for under-parameterized case and over-parameterized case. There is an analytic solutions. And to calculate the variance, you need noise epsilon. You can also Gaussian noise. Then variation is given by this formula. And for P is large, very large, you can use NP distribution. To calculate this trace. And after using that, you can obtain this variation formula. So variation is a function of P over N and variance of Gaussian noise. It is well known in machine learning field. To calculate this formula, they use a stealth transformation from NP distribution. Using this formula, we obtain S0. And from S0, one can obtain variance. You can consult with this very nice book of picture. Yes, this is how to calculate the error. And what is the relation with black hole? President Kim noticed that in Page's seminar paper, equation 25 is just NP distribution. So I didn't know that. So we are surprised and try to apply our work on double descent to this black hole problem. And we searched the literature and found many related work. Many pieces already used the NP distribution describing black holes. They often assume that total state of the system is product of internal black hole state and radiation. And density matrix of radiation is given by reduced density matrix by tracing out the internal mode. Similar distribution also arises in grand matrix, which is the overlap of two internal black hole states. In many asymptotic ADSR, we call state time with or without angular momentum and supersymmetry. I don't know how they calculate this, but they argue that this kind of distribution is very, very universal in black hole physics. So it means that, in short, density of eigenvalue of Hawking radiation often can be given by NP distribution. Then from this NP distribution, you can easily obtain entanglement entropy. And it follows the Page curve. So if Hawking radiation satisfies this NP distribution, Page curve comes easily. It was done by other people. And interestingly, this entropy has inversion symmetry. You can change the role of N over P or omega or omega and exponential S. Strange they has a symmetry.
So alpha was the ratio between N and P, right?
Yeah. In machine learning, P over N. In black hole, it is omega over exponential S. Ratio of dimension of Hawking radiation and black hole. In black hole case. They believe quantum machine learning can outperform classical machine learning, but it is unclear. Linking quantum machine learning with the black hole is not new. There are a few works about this one. One of the problem of quantum machine learning is called so-called barren plateaus. It is the flat region of cost function. So if a system is in flat region, you cannot find a way to the minimum error. That means it is very hard to train the machine learning. And in this work, they show that extracting unknown, learning unknown internal black hole system encounters often barren plateau. And in this work, you can find other works. Oh, okay. Finally, our work. So we assume that quantum linear regression using the black hole Hawking radiation as a density matrix. In quantum machine learning, you can encode the classical data into density matrix. So in a sense, beta is kind of plays a role of small x here, and we want to find this beta value, and beta value represent the internal state of black hole. We are considering very specific case.
What is F beta?
This is model function, linear function.
What is W? W?
W is a weight, something like a slope.
So trace rho beta W gives what? F beta.
Who is density matrix?
Yes, density matrix. So in classical linear regression, you want to find the function, something like find this one, and in our case, in quantum machine learning, I want to find something like so I want to mapping like this one. A linear function.
What is physically W? W, what is
So is Hermitian observable.
observable?
Yeah.
Any observable?
We find this observable. So this scenario is just mathematical, not some practical one. For a given data, you want to find these observables, which gives correct y values. You are given by
Was beta is I don't understand. Psi beta, psi j is the same internal state, and beta what is beta?
beta is index for black hole internal state. So
Then what is I?
So what is the difference between I and beta? So
yes,
the state has two
that's the one. Beta represent the internal state of black hole. I represent the Hawking radiation state. So beta psi beta j means beta internal state entangled with j Hawking radiation. And so you are giving this training data, and to find the W. You can change the W. So in a sense, W maps Hawking edition state to internal index beta. And we assume for simplicity, diagonal operator. And assume observer has full knowledge of black hole physics and internal state. So it is not so natural, practical, but our estimation is purely mathematical one.
Yeah, you assume, do you assume? Yeah.
Yeah.
Oh,
So it is not a practical machine learning, not political.
we assume observer has a full knowledge. Yeah, assume.
Yes.
Why don't you prove? I wish you prove this one. Why don't you assume? We assume.
Here?
Why?
Why? Actually, this our scenario is just a mathematical one.
Because the
No
training
practical.
data is the state of the black hole, so you
Yes, that's
know the
right.
training data.
Yeah. Training data itself is the black hole internal state. So it's somewhat different from simple example. Referee also pointed out. Yeah. So from internal gram matrix, you can obtain this D matrix, which is similar to large X in classical linear relation. This is target. In this scenario, we are thinking that very good observer knows all these state and training quantum computer,
Super observer.
super observer, training quantum computer using this data. And then using this quantum computer, human or poor observer can test the radiation and try to find out the internal state. That kind of scenario. So after this construction, we can follow the case of classical linear regression.
And who is the super observer in practically? We are literally outside the horizon.
Jae-Weon Lee.
You are.
It can depend on the believer. Yeah. So we derive the variance, which is just the production of classical case. But it seems the first time somebody derived the double descent in quantum machine learning, although it is somewhat trivial.
So y vector is also y1 to yn or yp?
Each y is a number.
And
Uh,
each y is a product.
y1 is a number.
So
n
n
is
is
This is not a double descent behavior, only a single descent, because alpha is larger than one.
Single?
Alpha is larger than one, so this thing is monotonically decreasing. Y state is a double descent.
Sorry. When alpha is smaller than 1, V goes like this one.
Okay.
Yes.
So two different branches.
Yes. V is not the total error, it is just
Yeah,
variance.
Maybe it's the first descent. This is an ascent. Okay?
Yes, we need bias, which we did not show.
Okay.
Bias decrease first. And so we did not study here. If our scenario is correct, maybe here is something here we did not study here. So we can draw the variance. I did not show bias here, variance only. And this is a phase curve. And yeah. We are exploring a parallax black hole formation paradox and double sand phenomena. And this correspondence is somewhat too far. For, we are suggesting this correspondence. Dimension ratio alpha corresponds to Hilbert space ratio in black hole physics. It corresponds to P over N. Phase time corresponds to interpolation threshold. And length of density matrix is important. I skipped that point, but number of independent eigenvalue is important for
In black hole physics, to determine the phase time, we have to know the temperature. And what about in quantum machine learning side?
Yes.
What is the temperature corresponding to temperature in black hole?
I didn't think about it. That can be important. It's just primitive work.
Here, you mentioned information retriever. So what is the definition of information here? How to
Information.
quantify the information?
Information is dependent on the category, but in quantum information, usually we think that information is something we can know from density matrix. Anything from density matrix. That's the information. Visual sense. So in this case, from Hawking radiation, we want to know something of internal black hole state. I will show some response from community. In this journal, they encouraged us to improve the explanation of known algorithm. But in this journal, just because you can map black hole parameters to ML parameters doesn't mean you take up the subject. Sometimes it just means you find a clever way to waste various time. Sorry for wasting your time. So actually, there are many works relating quantum information to
Either
this.
previous two things from where, what is the source? Is it in the central?
It is
Quantum inside.
it is quantum information journals. Yeah.
Below citation is
This this is some
impact on one thing.
I don't know, but everybody say something, everything here. Yeah.
Medium is just a IT industry journal. Quantum Insider is especially for the quantum information journal, the magazine. Different. Medium is usually focused on the AI, blockchain, or like a usual IT magazine. So that's why the Medium article is, maybe not written by physicists, I think.
They do not know the black hole.
Finally, I introduced the other famous work by the others. All these words are related to this paper. In this paper, Wilson et al. Argued that finding complexity in quantum computing is related to gravity, finding minimum path. And Susskind argued that quantum complexity is related to action of the gravity. And why AI science won Nobel Prize in physics? It is Hopfield showed that you can make AI using spin, and one of the important achievement of Hinton is using Boltzmann machine. Boltzmann machine is a thermal version of Hopfield model. And using IBM, you can extract information of large system to small system. It looks like kind of a renormalization. And this renormalization group approach, they show that variational renormalization group is similar to Boltzmann machine. Boltzmann machine is kind of deep learning. And these people argue that this ADS-CFT correspondence is similar to error correction or deep learning. So I argue that quantum field itself can be viewed as deep learning. Similarly, I try to argue that linking deep learning to physics is not so crazy idea. There are many attempts to. Yeah, that's all.